Alright, this lab is a little bit difficult, so I think I'm going to help you with it. So for the first one, we're trying to find the CP of iron. And you have a metal washer. And so what we're going to do is we're going to put it in our container. And let me just draw this. So what the idea is we have a container, a calorimeter, into which we put 100 grams of water. And then you're going to put a washer into it. And what's going to happen is energy is going to flow out of the water and into the washer because the washer is cold and the water is hot. So as energy leaves the water gets colder, and as energy enters the washer gets warmer, and the same amount of energy that leaves the washer goes into that leaves the water goes in the washer. So let's just try this. Okay. So we got is the mass of the water is 100 grams. And when I measure the mass of my metal washer, I got mine to be about 31.5 grams. Now, you might have found something different for yours because they're all different. Now, the starting temperature of the water, again, yours is not going to be the same as mine, but when I did it, the starting temperature of the water was 23.4 degrees Celsius. And the starting temperature of the metal, since it's in water, we'll assume it to be 0 degrees Celsius. Now, what we find then is the water is going to cool down when I put the metal in it. So the washer goes in, energy flows into the washer, leaving the water, so the water should get colder and the metal should get hotter. So what we find afterwards is the ending temperature of the water I got to be 22.6 degrees Celsius. And since the metal must be at the same temperature of the water, I can record, even though I can't actually measure it, I know that the temperature of the water is also, oops, that's not good, is also 22.6 degrees Celsius. So that's one thing to keep in mind. When you do these calorimetry problems, the ending temperature is always the same for both. One starts out warm and one starts out cold. But when they're done, they're both at the same temperature. That's why it's not changing temperature anymore, because they both are at the same. Now what I have to do is calculate the delta T, the change in temperature for this one versus the change in temperature for this one. And all I had to do is take the difference between these two values and the difference between these two values, and I want the absolute value of it. I don't really care if it's positive or negative. So what I find is that the water changed a whopping 0.8 degrees, and the metal changed 22.6 degrees because it started at 0. Now what I'm going to do is I'm going to find the delta Q of the water, and I'm going to use this value to do it. So to find the delta Q, I have to take the mass of the water, which is here, the delta T of the water, which is here, and the CP of water, which is 1. So let's just go ahead and do this calculation then. So what we're going to have here is, I'll do it over here, that the delta Q is going to equal the mass of the water times the delta T of the water, which is 0.8, times the CP of water, which is 1. And when I multiply all those together, what I get is a delta Q of 80 calories. So I'm going to put 80 calories here. And what I've got to remember is, the way calorimetry works is, the water lost 80 calories. It gave those calories to the metal in order to warm it up. So the 80 calories that the water lost is the same 80 calories that the metal gained. So when we do calorimetry, the delta Q is always the same for both substances. Now, my next thing I was asked to do is find the specific heat capacity of iron. Assume this is an iron washer. Well, to find the specific heat capacity, I have to know the delta Q, the mass, and the delta T of the metal. Now, the delta Q of the metal is 80. So I'm going to say 80 equals, the mass of the metal is 31.5, and the delta T of the metal is 22.6. That's at 22.6 times the CP, which I don't know. Now, what I've got to do now is I've got to get CP by itself. That's a terrible CP, but that's CP. What's being done to it? Well, it's being multiplied by 22.6. So what I'm going to do is I'm going to divide both sides by 22.6. 22.6. And that makes this go away. Then what I have to do is I see now that I've done that, CP is being multiplied by 31.5. Well, what's the opposite of multiplied? Divided. I have to divide both sides by 31.5. Divide by 31.5. So if I enter into my calculator 80 divided by 22.6 divided by 31.5, I'll find that I get a value of 0.11. And now the specific heat capacity units are going to be calories per gram degree Celsius. In other words, to change the temperature of iron, it takes 0.11 calories to make 1 gram of iron change its temperature 1 degree. Oops. Now you know I am not going to go ahead and I'm not going to really bother to do trial 2. I mean, you have to bother to do it, but I'm not going to do it because you know what? We're going to find it is the same. But one thing you should notice is that the CP of lead should be considerably lower. So if you've done it correctly, you'll get a value that's less than 0.11 because lead it's easier to change the temperature of lead. So if I look at the last question down here, then it says if I have a 100-gram piece of lead and a 100-gram piece of iron, so I have the same mass, they both start at the same temperature, and I let them cool down. After several minutes of cooling, which one will be hotter to the touch? Well, the one that's going to be hotter is the one that cooled down least, the one that's harder to change the temperature of. And if you've done it correctly, what you should find is that the iron has a higher specific heat capacity, therefore it's harder to change the temperature of the iron, and that's why, for this one here, the answer is iron. Hey, wasn't this part fun? I hope you didn't burn yourself. Okay, so how hot is red hot? I'm going to use the same equation to do this here, but in this case, here's what I found. I started off with a mass of 100 grams of water, and you should have found that your copper penny had a mass of about 3.0 grams. Now, the starting temperature of water is going to be different for everybody. When I did it, I had 22.2 degrees Celsius. Now, I don't know what the starting temperature of the metal is because it's red hot, and I'm not exactly about to put a thermometer in it. But I do know that when I put that washer into the water, what happened was the temperature of the water came up as energy moved out of the coin and into the water. And what I found when I did it was that the temperature went up of the water went up to 24.1 degrees Celsius. And presumably that's still the end temperature of the copper penny as well. That's the way calorimetry works. We always have the same ending temperature. Now what I have to do is I have to find the delta T of the water. Well, the delta T of the water I'm going to find by taking 24.1 and subtracting 22.2, and that gives me 1.9 degrees Celsius delta T. Now, at this point, I do not know what the delta T of the metal is. In fact, that's what I'm going to solve for, and here's how I'm going to do it. I'm going to find the delta Q of the water, and I can do that just by substituting into this equation. I know the mass of the water is 100. I know the delta T of the water is 1.9. I know the specific heat capacity of water is always 1. So when I solve that equation, then what I'm going to get is 190 calories is how much energy left the coin and went into the water. Well, now here's the thing. The delta Q of the water is also going to be the delta Q of the metal because in order for the water to gain that energy, the coin had to lose that energy. So now what I need to do is I'm going to go ahead and I'm going to use this equation and I'm going to solve it in this case for delta T. So that means I have to know the delta Q of the metal, I have to know the M of the metal and the CP of the metal, which I happen to know all of these things. And let me just move this up a little bit. I think we've got this equation in mind, hopefully. So I'm going to move this screen up a little bit. And the reason I had to do that is because it was important for us to know that what we have here is what the specific heat of this is. So let's look at number 3. How much heat energy that the water gained from the red hot penny is right here. That's 190 calories. So what I'm going to do now is I'm going to say 190 calories, that's my delta Q, equals, now I'm talking about the penny, so it's the mass of the penny, which is 3.0 grams, times the delta T of the penny, which is what I'm looking for, times the specific heat capacity of the penny, which I was just told here is 0.092. 0.092. So what I have to do is I have to get delta T by itself. Delta T is being multiplied by 0.3. The opposite of multiplied is divided by, so I'm going to divide this by 3.0. That makes this go away. Now I see that in addition to multiplied by that, it's also being multiplied by 0.092, so the opposite of multiplied is divided by. I'm going to divide both sides by 0.092. And when I do that, what I'll find is that I get a delta T value of, when I did it, of 688 degrees Celsius. So I'm almost done, but not quite, because that's how much the temperature changed. But how hot was red hot? Well, what I have to do is take the what I'm trying to do is I'm trying to find what is the starting temperature of the red hot metal. Well, I know what the ending temperature is, and now I know how much it changed its temperature. So all I have to do is add this to find what the beginning temperature was. So 688, that's how much it changed, plus whatever it was to end with, 24.1. That means what I end up with then is around 700 degrees-ish. So as long as you got something around 700 degrees Celsius, you did a good job.